Okay, so I want to be talking about PAC learning, which means probably approximately correct learning. And this is a framework that is supposed to capture statistical learning, classification in statistical learning. So, and these notions are classically defined without any computability assumptions. And recently, this framework was studied with computability assumptions. And in particular, I've studied this with Sasha Kozaczynski, with Valentino de la Rosa, who is also here, and with Cristobal Rojas. And we have some observations that I would like to share. So, what is going on? We have some, as an input, we have some numbers. Well, these numbers might be from, suppose, real numbers, but for simplicity, let's assume that we are only working on natural numbers. So we see some numbers, and also we see some labels, which are binary. So each number belongs to the set or not. And our goal is to seeing a finite set of samples to output some hypothesis, which is a function from natural numbers to the labels. So we see a finite prefix of some function, and we want to guess the function. And well, we'll be interested in okay, guessing the real function might be hard, so we allow ourselves for some kind of for making some mistakes. So we want to have a function that is at least close enough to what we are really seeing. So we'll be allowing for an error, and we consider first the empirical error. So we have some sample and some objective function, and the error is just well, we look at sorry, the error with respect to, of course, some hypothesis is we look at all the things that we have in our sample, such that, and count all these guys that we predict wrongly. So f of x not equal to h of x. This is just the so-called 0-1 loss, and then we take the average. So this is the empirical error, something that...
But how the sample is connected? It's x1, x2, x3, and so on, or not?
Yes. So we take all the x's, x1, x2 in the sample set. Yes, so this is...
And values of y's are just values of function f.
Yes, the objective function. Well, so yes, S is a form x and some f of x. Well, this is one thing, but ultimately we'll be interested in not how well we are behaving on the training data set, but we want to be to talk about our error in general, also on the data that we haven't so far seen. So we'll have something that it is sometimes called a generalization error. So I write it like that. I have some kind of distribution on natural numbers, D, and again, objective function. And I apply this to the hypothesis, and this is just the expected value of, expected value of X.
There's a probability that F is different from H on a random element of D, yeah?
Yes, exactly. So
Yeah.
this is L X F of H, given that distribution. So our goal is to minimize this particular value. And so why is it called statistical learning? Because we get the samples, and the samples are we assume that we are sampling the samples IID, so with the same probability independently, and we are, of course, if we sample more and more, we can expect that our empirical error will be getting close to this generalization error, but we would like to have some universal bounds, because of course in general in this setting we are assuming that we don't know the distribution, and we would like to have some bounds that whatever distribution we are seeing and whatever objective function is, we can have a uniform bound on which tells us how many samples we should take to know that we are making small error with sufficiently big probability. So to be precise, let us introduce the notion of PAC learning. So a class H, which is a class of function from natural numbers into label 0, 1,
Yeah.
is called PAC learnable if there is a learner A, and the learner is a function which takes finite set of natural numbers with with labels and output hypothesis. Well,
so we have no assumptions what the class H is, so the function is abstract. It's just it gives H function from H and it's an abstract object, no polynomial time requirement, something like this.
No, so far not.
So far not. Okay.
We are just trying to see if we can always find a hypothesis that will be good, and we will.
If there is a learner A with some properties, just say the property.
Yes. Okay. So there is a learner A, such that.
Wait a second. Just write the image of A. Is it H or not?
It's part of H.
Well, it's
to H. Yeah.
It doesn't have to be H. So it's all the function.
Just some part of H. Yeah, it's function to H. Yeah.
H. Yeah.
Well,
no, I mean it could be also outside H.
Yes, that's
so
the point.
In general learners are
outside H, so any function.
Yeah, so just 0, 1 to natural numbers.
Yeah,
I guess.
Yeah. Yes, yes. So it's basically a subset of natural numbers. Okay, so there is a function m of n called sample complexity. Such that for all distributions on natural numbers and all functions f, we have that the probability with respect to d.
F is from H, right?
No, f
No.
can be also an arbitrary function from.
But what is the role of H?
No,
then?
f has to be from H. So the true function has in the
If
definition,
f is
all
not from H,
Yes,
why
definitions.
okay,
do we
yes,
change
yes.
it
Oh,
all?
sorry, of course. Yes, I'm sorry. F has to be from H. Yes, of course.
No, it doesn't. Well, H is not, the condition on H is not yet here. When F is from H, it's a realizable case, what we call.
Oh, sorry. It's yeah, you're right. But okay, original definition from Valiant was polynomial time, realizable case, and Oracle access to data training
Okay.
set. So
Okay,
yeah,
let F be
Yeah.
not in H. So what?
Okay, yes, okay, right. Sasha is right. It doesn't have to be from, so it's just a function from natural numbers into 0, 1. So what we want is that the probability with respect to the distribution of, so we, okay, that's not enough, sorry. So for all functions and all if we sample a sample which is of size bigger than m of n,
According to distribution.
according to the distribution,
Yeah.
then the probability of having a generalization error with respect to the distribution and this function f of the hypothesis that our learner outputs when seeing S, this thing is supposed to be close to the best one, best hypothesis. So with respect to all hypotheses in the class, with 1/n error, and this probability we want it to be big.
But what is the mean? Why it's kind of strange? Why we compare the best hypothesis in H with our hypothesis, our conjecture, which is not in H? What is the? Why do we do this?
Well, because we are interested in outputting, well, we want to guess a function.
In H or not?
Not necessarily in H.
Yeah.
So as we will see, because I will have to do a little bit of the classical theory, and as we will see in a moment, if we would allow for arbitrary functions, to compare to arbitrary functions, then this PAC learnability is not possible. So to be able to have learning in this sense, we have to have a strict class of hypotheses, which we take as a point of reference. But whether we output something that is in this class or not, in general setting, it doesn't matter, but in computable setting, it will matter. And I hope I will also say something about this.
Yes.
But, okay, can you explain
first,
for the beginning, for start,
yes,
why
but
the class
can
of all function
hello,
is
can you
not...
hear me?
Yeah.
Can you hear me? Yes. First, make the definition of LDF, the loss, clear. There is expectation, and then there is something strange under the expectation. So the distribution is over input-output pairs, right?
No, I understand that this. So we take randomly a sample of distribution D of size f of size m of n, and then we take all the values and give it to our learning algorithm.
Yes.
And we see what the learning algorithm gives us an answer. Now we try to estimate the effectiveness of this algorithm on a random element of D, and it should be as good as the best algorithm is in this infimum. With high probability, the probability is chosen under the first sampling over D. Yeah.
Yes, yes, inputs, so the X's are chosen a sampling over D, but it's again so first, there are normally simple complexities for realizable setting. I've never, there exist a few papers that define it for agnostic setting, but then the labels are also random. And so there is some definition in intermediate, which I've never seen. So where does this definition come from?
Well, I
This
don't know.
definition?
It's all the same, no?
What
Because
is
it
the
doesn't
same?
matter.
Yeah.
Well, okay, if it's all the same to finite VC dimension, then
Yeah.
okay, it's the same. But for polynomial time, it's different story. And
Yeah,
also
sure.
you can think about finite variance where you limited the access to finite set. And also it's the values of sample complexity are different.
But if it's important for us to understand what are the two different stories,
no, it's not
I inform
important.
you that I understand only one story and very basically. So first I would like to see some example of class which is not learnable and class which is learnable. Just for example.
Yeah, okay, my complaints are not so relevant, by the way. It's just about literature.
So learnable class is a class consisting of one hypothesis. You just always output one hypothesis.
No, why? Because if you output this hypothesis, you are very you do the best you can do in this class H.
Yeah, I mean, even if you have a finite class of hypotheses, then it's also learnable because no, it's not clear why. Yeah, but it's requires some argument, but it's
Sasha, but I think that this is quite non-standard, your definition. For example, it is known that the set, the class of disjunction is learnable. And why is this?
What do you mean by the class of disjunction?
No, our H is the class of functions of the form x1 or x2 and so on. Where
I'm not so sure it's learnable. So why do you think? Because it's infinite domain here. If it's finite domain,
it's a different thing. If you have a polynomial, yeah, you say that you are interested in the algorithm, but here is a fixed domain, and then everything over a finite domain, I guess, is learnable in this definition.
the definitions look strange, because usually when you say that a class is learnable, you mean that the target function f, which is f here, is taken from that class. So you restrict the set of all functions to a family of functions. And you know in advance that your target function is from that family. This is a normal definition, normal setting. And
Well, I mean,
in your
I don't know.
setting, the target function, we have no idea what it is, right?
Yeah. And we just want to do at least as good as, so I mean, we can have H and we can assume that our F is, you know, is close to the H. And then in that case, we kind of, in the setting that you said, we cannot do anything. But here we still might want to do, to approximate our function well. And then,
So anyway, have you seen this setting in the literature, or it is just
yes.
your invention?
Well, it's well known that it's all equivalent, so it doesn't matter, and it's all equivalent to finite VC dimension. That's the whole
non-effective setting.
point.
Yes.
In non-effective setting, and then in the computability setting where the learner must be computable, that might make a difference. Some aspects make difference, some aspects not, and that's basically the what we are trying to do, to figure out which aspects matter and which not.
Okay, so let's just remember that a strange definition. We learn some functions, arbitrary function, we provide some arbitrary functions, I guess, but the quality is measured just compared to the best quality, which is achievable from class H, whatever it is.
Yes.
And there is also a thing, you call the function sample complexity, but it's only connected to confidence and not to the size of the training set. So it's very misguiding word sample complexity. It should be like confidence complexity. So function MN, oh, sorry, I misread, sorry.
Yeah, n is a confidence parameter, so it's like m of epsilon. Well, we just
Yeah, sorry, and size of set must be bigger than m of,
yeah.
Well, to summarize this discussion, we'll indeed make a difference between two types of learning. So if okay, well, okay, so if A is indeed a function from these natural numbers into H, then we will say that it is properly learnable.
H is properly learnable.
Yes, that H is properly learnable.
Wait, I think we can understand it using, you said that this is equivalent to having finite VC dimension, right, Sasha?
Yes. Yes.
Can you then demonstrate how to learn the set of half planes?
Well, what do you mean? To prove
I mean the classical example of a set of with finite VC dimension is hyperplanes, right?
Yes.
But now we have even infinite natural numbers without
That doesn't matter.
instructions.
So assume that our n, our natural numbers, are considered as square, n squared. This is the same, and assume that H is the family of hyperplanes, right? Then we obtain a set of functions, and how to learn it? It has finite VC dimension, as we know.
So I guess there is no easier way than just to prove Wapnin-Chervoninka's theorem, right from the start. In that
Really?
case. Well, I mean, if the half planes are if they are all going through the same, like I mean, if they all go from the origin through the origin, then I think it's possible to show it easier than this. But if not, then it's not clear how to do without this general.
Okay, assume they all pass through the origin. Okay, and what do we do then?
But then it's kind of threshold classification. It becomes like you're on a circle. So it would be nicer to speak about a line and a threshold in this example. It's almost the same. But
Yeah.
also, yeah.
So
but
basically we have, yeah, so we have some unknown number and we receive some.
Okay, we receive some points on the plane. I mean, we not the points. We points and 0 or 1. So we are given information that 5 points are in our set and another 7 are outside the set. So we want to find that threshold, right?
Yes.
How do we find?
Then just find the threshold which agrees. Well, I mean, if you are assuming that they actually come from a threshold, then you just find a. Well, okay, let's just consider the case when when the objective function is from the class. Okay. And then you just say that you take any threshold which agrees with the sample. Then you kind of argue that
of course, it can be that there is no threshold that agrees with the sample.
okay, I'm saying in the case when objective function comes from the class.
Ah, sorry.
So then there exists, and the point is that you can take any. Because,
is it okay if I draw something? Can you see if I draw something?
But where do you,
Yes.
yeah.
Yeah, okay. So imagine that a function is from, so we have a true threshold function. So T is some threshold. So here we have 1 and below we have 0. And then we will receive some points from S. And let us take, for example, as our function H. H has a threshold, which is the lowest value, that is 1. Let us this as classifier. And if all the points that we receive are 0, we answer constant 0. So here we have 0. Okay, and then we have to look at the distribution over the inputs. So now let us think about D, and let us look, let us play some, so I forgot to usually there is some epsilon, some threshold here, 1 over n it was, right? We had this 1 over n. So there is, let us look at the smallest position where probability is at least 1 over n. So here is a
Yeah.
special position. And so when will our function that we produce, our function h, when will it be bad? It will be if we have no sampled points that are sampled in the special region. So we are allowed to use n random samples from D. Okay. And we will choose h. The threshold of h will be the lowest one, the lowest point that's equal that label 1. Okay. So what is the procedure? We create S. Sorry for the lines, there is something wrong with my right button.
So you claim that n samples is enough, right?
Oh yeah, sorry, n means something else. So sorry, we have m samples. I don't know yet what is m, but let us think about. Let us derive condition that will be good
Well,
enough.
it's more or less n, yes.
Yeah.
Because you have to, well,
It
basically
will be log
sample
n.
n times to obtain, yeah, something from this interval.
N times log. Yeah, you're right. Yeah. So as okay, and so what is bad situation? Bad situation is that D is large in a region, but we have no ones here, because then we will place our threshold too high. And then in a test sample with high probability, we will get a point from here and misclassify it. We think it's 0, but it's 1. So do I get it? Because everyone looks tired now.
No, but I just what you are explaining. Say it again.
I'm explaining what is the learning algorithm.
For
Let
which
me
class?
restart.
For which
For
segment?
Class
threshold
of
function.
threshold.
So threshold, you mean that just for natural numbers, they are compared with some threshold.
Yeah. So what is H? H is the class
Of threshold, that's clear. But you prove that it's learnable in the sense of the definition which was before, which original function is not in H, and other functions are not
No, but
out.
now we first explain for realizable setting, because non-realizable setting, we need extra tool, Chernow bound, and it's not so easy to explain directly.
So the function is from H. So there is some true threshold. Then we take to find this, to learn this threshold, we just try randomly some elements of D.
Yeah.
And of course, seeing these elements of D, we know somewhere where the threshold is. It is between something.
Yeah.
And
Yes.
we choose some element, our threshold somewhere there. And we hope to be lucky that our test element will be in the same, not in the same bad position.
Yeah. So we hope that all, So we will pick threshold here.
Yeah.
Smallest, that is 1. And so we will say that A of S equals, this line. The threshold function on this line.
Yeah, and now you want to say that this new element has equal probability to be the first element, the second element, the third element, and only in one case there is a problem with threshold. That's what you are planning to say.
That's leave one out technique. Yeah, that's indeed. I want to say slightly different thing, because we need to prepare for other setting. Okay, so that's what we see. And now it can happen that the true function from H, this F has its threshold here. And so where is the place where we get a new sample? So in the definition, we have to look to test sample.
Yeah.
After training, we get new samples taken from the same distribution D. And so this test sample, if it's above this line, we are good. Here it's okay. If we are below the threshold, we are also okay. But we have a problem when we are here. Sorry for my right, but. So here we have problem.
Yeah.
That's the region where we are wrong. And so it's important for us that we have So we can now, we have a target probability. We have the true threshold, and we look to the position where probability of measure D is at least 1 over n, the smallest place where it's at least 1 over n. And now we have to bound probability that we generate a best test set, best training set S. S is bad. What does it mean? That this lowest positive example is above this line. Then S is bad because the hypothesis produced by A of S, makes a mistake with probability more than 1 over n. Then we are bad. So when we go back to the definition, we assume, so there is an error on, so we have the loss of, we had this loss x over d of A of S. The condition is that it has to be larger than something that is 0, because we make a special assumption, plus 1 over n. And so this probability had to be smaller than, has to be larger than 1 minus this. So that was our definition, right?
So here you put 0 because you're considering the realizable case.
Yeah, indeed. So we assume we only consider f from a
from H.
Yeah, yeah. So that's why I say let's think that f is here, has a threshold here.
So
Okay.
there is some, maybe you can comment. So there is some strange thing. So we can just consider a new element from D and take a probability, general probability that the answer will be incorrect. But you somehow split this probability using kind of Fubini theorem. This should be smaller than 1n over the last choice, and probability of this should be bigger than 1 minus 1n over the first choices.
Yeah, I repeat the definition that was given by Tomasz. It's right, okay?
But why do you split it in using Fubini? It's kind of...
No, I repeat his definition. I
No,
have
yet
no
I
choice.
understand, but why you use it? Why you and he and everyone use this definition?
Which
Somehow.
definition?
No, first I teach this in my course and I do like you say, because I think the same thing. And then at the end, I tell to the student, you can split. And today was commission, and they actually told me I should not teach PAC learnability, the other teachers. They think it's outdated because they're from machine learning foundations. But okay, that's not
That's
relevant
another story.
now.
But so it is the same, it's equivalent, more or less.
Yes, it's equivalent.
Can you say, Sasha, can you say again, which definitions?
So you can
mean
consider
like
a definition like this. So you take a learning sample,
Yeah.
and you apply the learning algorithm, and then you take one more sample and you see whether you are right or not.
Yeah.
And there is some probability of error, which depends both on the learning sample and the final test sample, test element.
Yeah.
Instead of this, what you are doing, you split this probability into kind of two projections. So you first fix the first element and see whether the probability of the last one being leading to a wrong answer is smaller than 1n. And then you take the probability of the sample to be 1 minus 1 over n. Oh, you can do this. Just maybe you can, because I am completely I don't know anything about this PAC learning, so maybe you can somehow comment why you do it.
And so then this example is very easy because you have the simple bound of s plus 1, because what you take here, you take n plus 1 point, and then you can like randomly permute them to select x tilde and let the other one n wants to be s. And only for this one special point, when x tilde is the smallest value that equals that has positive label, you make a mistake, and so you directly see that this probability is bounded by 1 divided by size of s plus 1. So that's what you were trying to say.
Yeah.
And you complained, why do you do this
And
complicated
but
things?
what you are saying is somehow at least it's not a corollary. This Markov inequality is not enough.
No, Markov inequality should be enough.
No, you don't have square
mean
root of n.
2D?
You have 1 over n.
So you should be careful. So the size of s is indeed n squared. So you should, and your explanation. So we will find that m, the size of s, is equal to n log n, and with your proof it's n squared. That's true.
And this is true for m is equal to n log n.
Yeah.
And why? It's difficult result or
No, it's easy.
It's already explained.
Finished.
But
Yeah,
just repeat the
almost
explanation.
finished. Yeah.
For stupid people, you should do it several times.
So I will remove this, but somehow it does. There is a delay. Okay. Okay. So when I wanted to explain when we can have bad luck in our training set. It can happen that training set is not representative, regardless of how big is m. Maybe m is 2 to the power n. We can have bad luck because we only get irrelevant training points that are very high here and very low zeros here. While on the test, while D is quite uniform.
Yeah.
Okay, and so what is bad for us? So there is a special region where the lowest part, where the true labels as 1, and that has 1 over n. And if none of these points are in S, then A of S is bad. And so we have to bound this probability.
In probability of this region when 1 is replaced by 0.
Yeah. Probability S is bad.
Small.
Yeah. Okay, so we will bound it. Probability that the first sample is bad is at least 1, is at most 1 to minus 1 over n. And so probability that all of m are bad is at most this thing. So m samples, so S is taken. So S is taken from dm. Probability that all m samples avoid this region, 1 minus 1 over n to the power m. And now we can bound it by exponent m times 1 over n with the minus.
But S is not fixed, it's somehow a random variable. Why the probability that this is bad?
So S is obtained by taking m samples from the same distribution D.
Yeah.
And so for the first, what is probability that x1 avoids this region? So what do we know? It is at most.
The region depends on S, yeah?
Yeah.
Or I am missing something.
No, region does not depend on S.
Sasha, the region depends only on the probability distribution.
And the true function, that if we fix true function and probability distribution.
Yes.
Yeah,
right.
but then explain again what is the region. I thought that this was the region when 1 is replaced by 0 in our sample.
But, no, that's in your argument.
Yeah, but what is the region then?
In other argument, it's defined by the smallest point, so that this interval has probability at least 1 over n.
With respect to our distribution.
Yeah.
Mm-hmm. Yeah.
So now this region is fixed. And what is probability that a random point from D avoids this region?
Because they are independent, it's a product of 1 minus 1 over n. And
yeah. And then you need n log n because you have 1 over e, and then you need to get 1 over n.
And if we consider not realizable case, do we just take the best threshold? I mean, with the best empirical quality,
Yes.
right?
Yeah, yeah.
Yes.
So, and do you know any cases when the learner outputs something outside H?
Outside.
What do you mean outside H?
In
No,
this
in our
example,
setting,
our
we
learning
Okay.
algorithm outputs.
Well, there is a
something
result
which
that
is in
if he
H,
can
right?
if there is a learner which outputs outside the set, you can always have a learner which outputs inside the set.
Then why have you such a general I mean setting when you write that the learner outputs something in any function? Why not just to say that the function is the goal target function is in H, if it always occurs, actually.
Well, what
Well,
Sasha said is true for the non-effective setting, where we don't care about the how strong is the learner. But once we put a restriction on the learner, then this thing might happen.
Ah, I see.
So maybe this is a good moment to actually see an example.
Yeah, okay.
So, for instance, suppose that we have a class of hypotheses H, Ij, which are defined like that, of X, of course. So it will be 1 if X is to I. It will be 1 if X is to J plus 1 and 0 otherwise. And now H, let it consist of functions of this type such that J encodes a proof of its formula of, for example, piano arithmetics. So a sufficiently expressible theory which will be undecidable. And now,
Okay.
now suppose that we have a distribution.
so this is let me say, this is an example where we need to output something outside the class if we want the for computable setting.
Yes. Okay.
That is needed.
So yes. I will. This is in computable setting. I ask the learner to be computable, and I want to show that if we ask for proper learning, so if we want to output something from the class H, then this won't be possible. At least not with the uniform bound that is required in the definition. But if we allow for outputting something outside of the class, then there will be a very then there will be a learning because, well, as we can see, this class has a finite VC dimension. So it is learnable in this. Well, so I'm sorry for a person that don't know, but for people who knows this PAC learning, I will introduce the VC dimension later. So for people that already knows it, we can see that this class is learnable in at least in non-effective.
Yeah, but maybe you can say how in practice we learn it. So we have a sample, and if there are two ones, that's clear. If it's only one of the second type, then we can find the one of the first type. But
on some 2i. So
Yeah.
if I see a sample 2i with label 1, well, I would like to output a hypothesis which also says 1 on this point. But to know if I have this hypothesis in my class, I have to know if there is a proof, if the formula encoded by I has a proof, if it's a theorem. So suppose that I really can learn, well, then I can decide the theory, the piano arithmetics, because I just do this, sample this distribution long enough, and how long that depends on the sample complexity, and I'm able to answer in finite time the question whether given formula has a proof or not in piano arithmetics. So in proper learning, this is not possible. But well, if we consider a
Sasha,
learner that,
for example, was
Yeah.
it clear or no?
No. My understanding is you can try many elements of D. If you have 2 1s, that's perfect. If you have only 1 1 and it's even, that's a problem. Then you need to find the non-recursively find this J, or really it's something which happens with small probability. So if you take many elements of D and you don't see the second one, you can just say that, look, it doesn't exist. But then you will get something outside of H. That's what you are saying, or not?
Well, I mean, there is no probability, I think. So I mean,
I
so
mean,
there are a lot
reason
of
is-
things here. So first, well,
There is
first thing that
distribution
is
D
usable to understand is that if you assume that the objective function comes from the class, then
yeah,
it's
I assume that
computably learnable, right? Because you just
I assume that the objective function is in the class, but the answer may be not in the class, and then it seems to be learnable. And that's what was explained, or not?
no, even if the answer is from the class,
It's learnable.
it's learnable. So it's learnable if you assume that the objective function is from the class, and
Why?
it's learnable. Well, you have a sample and you find anything which agrees with it in your class.
yes,
You just enumerate all
we
these
know-
I's and J's. Yeah.
Yeah,
Until we find something
but I don't know. Imagine we see only one place when there's 1, and this place an even, and we cannot find the proof yet. What do we do?
But if we are in assumption that H, that the objective function comes from the class, then if we have 1 on 2I, we know that there exists.
Yes, this is like we are getting a promise.
We know.
That this is a theorem. Then we just wait until we see the proof. But as Sasha
we know that the J exists if I is provable, but maybe I is not provable. We don't know.
Well, I mean, we are in
cannot search
assumption
for
that,
J.
Why we cannot search for J?
Because the H consists of all functions, even J's is even if I is not provable, then there is just no other one. No. Or you consider only the cases when formula is provable, and then you put always 2 1s.
Yeah.
Then I understand. Yeah.
All the hypotheses have these 2 1s, have this form Hij,
Yeah.
and we put in the class only the one that it's written here, only the one where I is a theorem and J is a proof for I.
Yes.
Yeah.
Yeah. So the other thing to understand here is when assuming that the objective function doesn't come from the class, well,
Yeah.
But you have to output something within the class. Then
Yeah.
it's not computably learnable. And so then there was some argument, and
And
maybe even
if
two
you are
arguments.
allowed with some small probability allowed to not give any answer at all, then it becomes learnable or not?
Well,
If you allow,
no, because our counterexample is an atomic measure where we just always get the same point.
yeah.
So we would have to be undefined always.
So at atomic measure is, yeah.
Yeah, we are just with probability 1 always sample and the same even number.
Yeah.
So the probability stops playing any role in this counterexample anymore.
Yeah, okay.
So if we assume that there is a learner for this computable learner for this thing in the setting where objective function comes out, can come outside the class, we turn it into a decider for PA.
Yeah.
So how we do it? We get I and we want to know whether it's from PA. So it encodes a provable formula of PA. Well, it doesn't really matter that it's PA or something. Well, it's just a, and then what we do, we take that I and we just get
Well, so we know that there is
we just take our,
a number of samples where with large probability we make error smaller than 1. So
and then we just put get this many samples of the form 2i1, 2i1, 2i1 to our learner.
Yeah.
And then see what it outputs.
Yeah, yeah. So it should output the same thing, and this same thing should, if it doesn't contain the correct j, then it's not.
Yeah, but if it's output a function, you don't know what are the indices I and j. So when you search what is j, it can take uncomputably unboundedly long.
Yeah. That's why it's not learnable. Yeah, why it's not computable.
No, but we assume that it outputs. So what the learner outputs some well, a Turing machine which computes the hypothesis that this
right. But so
and then
Turing
if
machine
we
is
assume.
So the Turing machine gets some x, and then it tries whether all values below x are a valid proof. It's right.
Yeah, but we promise that if we are assuming now that this Turing machine should output a function in our class. So we know that it has 2 ones.
Yes.
And we just find it by.
Yeah, but we already know that I is provable, so we can also search for the proof.
No, now I is not in the class. Now a input is not in the class, I guess.
Okay, let's again. So how we decide whether I is provable? We take sufficiently many guys of the form 2i1, then see what our learner outputs. It outputs some Turing machine for some function hij. We find these 2 ones. And then we look if this is actually
yeah, but we find
function.
these 2 ones, which can take arbitrarily much time.
Yeah, but to get a contradiction, we don't need a time bound.
But it's computable. I don't know. It's an algorithm. So I don't know. It's always it's not a it's a total algorithm. Like it halts on any input. So I don't know how it can take arbitrarily uncomputable time or something.
No, it halts if I is provable. And if I is not provable, we don't care when it halts.
If I is provable, it halts. If I is not provable, well, let me finish the algorithm. If the learner outputs something which has 1 on I, it says that I is provable. If the learner outputs something which doesn't have 1 on I, then it outputs that it's not that I is not provable. And it's and this decides piano arithmetic, because if I is provable, then the best approximation to that function is hij.
Okay, yeah.
And if I is not provable, then we don't have anything which has 1 on hij.
Okay, but
And the best approximation, I mean, all the other functions in the class, if you just consider objective function, which is just 1 on 2i, then if I is provable, then there is hij, which has 0 error, and all the other have 1 error, error 1. And if I is not provable, then all guys have error 1. So basically, your learning output algorithm should output something hij if and only if the I formula is provable.
okay, I see my mistake, because it's agnostic setting, and so you're allowed to use functions that are not from H.
Objective
An
functions,
objective
but
function,
output
yeah.
of the learner are from H.
Yeah,
Yeah.
but your counterexample doesn't work for realizable setting.
Yeah, in realizable setting, it's learnable. Yes.
Yeah, sorry. Okay, yeah, got it.
Yeah, and the final thing is that it's learnable even if for arbitrary objective functions when you can output something outside the class.
Yes, for instance, if you consider all the functions of form hij, whether they encode a proof or not. Then we just see if we, where we have ones, we can be correct at most, well, we can correctly output 1 at almost 2 places, and we just look for the hypothesis fitting it to the data. So this is an example that shows that indeed in the computable setting, it makes difference whether we are allowed to output the hypothesis in the class or something outside of the class.
Yes, I get it.
Okay, so I see I have a little bit more time yet, so there is a. I don't want to. I don't have time to go through all the classical theory, but there is one result that that we will use heavily in our characterizations. So this is something that they call no free lunch theorem. And this also answers a question how to construct a class which is not learnable even if we drop the computability setting. So let us take a learner.
But for example, if we take a class of all functions, it's obvious that's not learnable.
Yes, yes. I mean, I'm gonna prove it, or at least.
Okay.
So, but yes, it's not learnable, and well, so this is the basic observation that we cannot put too much into the class if we want to be learnable. So, okay, let us take a learner.
I mean, you are trying to prove that if finite VC, if the VC dimension is infinite, then it's not learnable.
Yes, but I mean, I want to first advertise why we want to define VC dimension. So what I'm gonna show is that, well, if we have a learner and we have too many hypotheses, then we can always find a hypothesis that will be adversary to what learner does.
So maybe you can even explain. So I don't know why the class of all functions is not learning. Just and then, or it's
well, I mean, a little bit hand waving. Well, so suppose we have some training data and some data that we want to test our learner with respect to.
That's only one value. Why you take many?
Well, yeah, sure. Okay, I can do it on one. Well, suppose I have I see some point X with label 1, and my learner is supposed to output something, and well, it will be a function. It's some function h that, given a second point x2, well, it will be, let's assume that it's 1. Well, then I can find a function that will be adversary for A, namely a function f that does the opposite. And well, if I have too many functions, then
But you should, in definition, you should take the function before you take the first element in the sample. So somehow it's in different order, no?
yes.
No, I'm sorry that I just probably anyone.
But I mean,
everyone else
imagine that
knows
you
all this, but just I'm.
No, Sasha. Just we can assume that the adversary chooses f, but
Yes.
and we can deal with that. But then assume that we just take f at random. And if we can deal against adversary who is choosing f, then we can deal against a random f. And then we just say that if we receive just one sample and we try to predict the next bit, we just have no information. It can be 0 or 1.
If the probability, if this new test point is outside the sample, then we should just probability to guess is 1/2. That's what you say.
Yeah, and then and then it's regardless how many samples you take, you know. If you just, let's say, consider some uniform distribution on some finite set, and then you take a half of samples, and you take samples on some uniform distribution on some set of size k.
Yeah,
and you take
the
k
size
over 2
can
samples.
be chosen after we choose m of n, so it can be larger than m of n, because the
well, I mean,
is after m of n.
What is m of m?
M of
this sample complexity.
Yeah,
we have to take, you know, supposedly our learner should, after, I don't know, 100 samples, it should learn with precision 1/10, and then we should take, I don't know, some set of size
just
200.
we have to choose the distribution after m of n is known. Yeah, that's what is important.
But it's just we need it just for some fixed number, like 1/10.
Yeah. So I agree that it's not learnable, but no free lunch theorem is something different.
It's a generalization of this thing when you have infinite VC dimension, then it's any class with infinite VC dimension is not learnable.
And it is not it is a difficult theorem.
No, it's the same proof. If you remember the definition of VC dimension?
Yeah, I think it's just you can find an element when you have for every n you can find n coordinates where all combination of zeros and one are possible.
Yes, exactly. And now you just take, you imagine that you just need in this
you
argument
take a
that
random sample for yeah.
You have not all functions, but all function on some 2k, on some for arbitrarily large guys
Yeah.
in your hypothesis class.
Yeah.
So
we
it's
take
an obvious theorem.
Yeah, okay. And so the difficult part is if VC dimension is finite, then something is learnable. This is the difficult part.
Yes.
Yeah.
Yes, and this I think I won't try to prove
Okay.
the whole. I mean, it is. So if the class of hypothesis is finite, then I suppose this is just a simple application of Hevding inequality.
You can easier prove it with Sasha's technique, with leave one out technique.
Okay. Now, if you don't want to prove it, don't prove it. Okay.
Yeah. Okay. So because
sorry, it's not true even. Yeah, because agnostic setting. Yeah.
Something, then we start to ask what is this. So if you don't want to skip something, you can skip it.
Yeah. Okay. Let me write the theorem that Sasha was advertising, the proof. So if we take the learner and some natural number n, then there is a distribution D such that sampling S of size 2n, we have that we are making a big error with big probability on this sample. So it's if we take so sampling and there exists a function f such that the error with respect to this, the probability of with respect to this distribution of well, the error with respect to D and F of what our learner outputs is larger than, well, 1/7, I suppose, and this is larger than 1/8. I mean, these exact numbers.
There's some assumption about A and N. I don't know. There should be some assumption.
No assumption.
No.
It means that if you take an objective function at random, sorry, so there exists, you can just say that there exists an objective function which is approximated by the
so
learner.
We don't do many things about class, about
there is no class yet.
Yeah,
you just say that if we have a learner, then if you take just any uniform distribution on 2n numbers and you give n samples from the distribution to learner, then there exists f which is approximated by this learner. And we use this observation to, in the case when we have a class which can realize everything on these 2n numbers, then the minimum of the error on the class is 0, and the error of the learner is 1/7. You know.
Yeah. No, it's quite mystical what are the 7 and 8, but okay. I think that I get some general idea of what is happening.
Yeah, so the proof goes more or less as Sasha was saying. Well, we will look at all the we take 2 endpoints and we considered all the distributions. Well, a distribution that is concentrated on these points and all the possible functions, all the possible labelings that can be that can happen on these points, and we want to see that the worst error that can happen is this. So we take the expected error with respect to the random function, and then just some manipulation.
We take so we use the random function f and then exchange the order of randomness. So if
Yes.
If for every...
So if we start with, well, I can try to draw it very quickly.
No. Okay.
So we first have we take the max, then we see that the max is bounded from below by the average with respect to all the functions. Then we change the summation so that we have an average expected error on given point for each point. Like we average over all points.
No, it's I think I get some idea, but still I don't understand why it's 1, 7 and 1, 8, but don't worry. Just
It doesn't matter, Sasha.
Yeah. I mean, the thing is that we can find some alpha and beta that it works.
Okay.
And I mean, but so the observation that we will be using is that if A is computable, then F can be found computably. And this is because, well, if we know that the bad guy exists, then we can just look, we can just calculate, and this generalization error is just a finite number. It's the average of finite number of errors, and we can just count all of them and see which is the worst, and we output one of these guys. So in the classical setting, we have this VC dimension, and well, I will say that the class of hypothesis shatters points x1 to xk if for every function on which takes these points and label them with 0, 1, there is H in H that agrees with F. So this was mentioned already a few minutes ago. That means that every labeling that is possible on these points, I can find a function that does this labeling exactly. And VC is maximal size of set shattered VC of H, let's say, shattered by H, or infinite if there is no max.
Mm-hmm.
So the point is that the classical theorem is as follows. H is PAC learnable if and only if VC dimension of H is finite.
And this is true for different definition for when we take a hypothesis from H, or when we take
Yes, because here, this is when we have no effectivity assumption, so there is, we can just assume that we are always outputting something from H, because allowing us to output something from outside H doesn't help us at all. So if we try to look back to this example where we had with proofs, this was not learnable in the proper sense, but it is easy to see that actually the VC dimension is finite and not bigger than 2, because all the functions had finite support. Every functions put 1 in 2 places, and it might be that if we look at the odd numbers, then given proof can be a proof of at most 1 formula, because it's just the formula that it ends with. So if there is no 2 functions that have the same 1 in 2 odd places, and at even places, well, we either have always 0 or yes, I think it's Sasha, correct me if I'm wrong, but I think it will be exactly VC dimension 2, right?
Well, it's VC dimension is at most 2 if we consider, well, just the class of all functions with at most 2 ones have VC dimension at most 2.
Yeah.
Because if you take 3 natural numbers, you cannot realize a function which is all 1s on them. Means that in that example, its VC dimension was finite, but it wasn't
But there was no computable proper learner. So I will have to finish in, I suppose, 5 minutes, because I have another meeting, but I can advertise do we continue next week?
Yeah,
if we continue then next week, then I would advertise what I would present next week. So we will. The reason that I've been talking about this no free lunch theorem, and that we can find a bad f computably, is that we can use it to define a sort of the effective VC dimension. So we can effectivize this notion and then save the equivalence from the classical one in this effective setting. So we will be able to say that class is computably learnable if and only if the effective VC dimension is finite. So this is something I will try to show next time. And also we can, maybe as a kind of a homework, I would propose to think about how to construct a class which is computably learnable, which is learnable non-computably, so it has a finite VC dimension, but there is no computable learner, even improper one. And the idea here would be that if we have this no free lunch theorem, the computable one, then if something is learnable, then we can always, given sufficiently big set of samples, we can output what labelings is not, what an example of a labeling that is not realizable. So we have a kind of effect notion of the computing a witness for a finite VC dimension. And since these learners are computable, we can try to diagonalize against them. And maybe I will start with this next time.